a solar flare, a power plant, and a magnet. What do these three things have in common? You're about to find out. You probably already know about the electric force. Positives repel positives and opposites attract and so on. But what you might not know is there's another force that magnets affect moving charged particles. This is called the Lorentz force. Imagine a moving charge and a magnetic field perpendicular to its motion coming out of the north end of a magnet. There will be a force, the Lorentz force, perpendicular to both of these. Take a look at this. I have here a magnet with its magnetic field pointing out of north and into south, up. And I've arranged for a current to run from left to right. There will be a magnetic force on that current perpendicular to both of these. Watch. Magnetic fields also affect free-moving charges like this cathode ray. As the electron beam moves from left to right, it's deflected by the presence of the magnetic field. But how can you predict which way? You can predict the motion of a moving positive charge by using the right-hand rule. Your thumb is the velocity or current, your pointer finger is the magnetic field or B field, and your middle finger, well, that's the force. Current, field, force. Current from left to right, field from north to south, force toward you. Current, field, force. Normally, we imagine that current is the flow of positive charge. We call this conventional current or Franklin current. But what if the moving charge is negative? In reality, it is the negative charges that move. If the moving charge is negative, then simply point your right thumb in the opposite direction. This is the right-hand rule for negative moving charges. A good way to compare the strength of two magnets is with one of these old computer screens. Simply plug it into some plain color image and hold a magnet up to it, and the screen will go haywire. Afterwards, the computer screen may be very messed up for a long time, so don't do this to any computer screen that you like. You can reset it by unplugging, so go ahead and do that. The image is formed when electrons flying from the back to the front hit the fluorescent chemicals on the inside of the glass. That's why you need all this space. The electron beam is deflected by the magnetic field, causing this RGB pattern error. A stronger magnet will show more of these disturbance lines. Because the Lorentz force is perpendicular to the velocity, charges moving in magnetic fields will go in circles. You can see this on an EM apparatus. Electrons boiled off from this heated filament are accelerated through a high voltage. They would normally come out in a straight line, but the magnetic field curves them around into a circle. The stronger the magnetic field, the bigger the force and the tighter the circle. Bringing a simple bar magnet demonstrates that it is indeed the magnetic field that deflects the beam. This is why solar flares often bend into circular loops. The ejected plasma is bent by the sun's magnetic field because it's made of unbounded electric charges. The circles aren't perfect, though, because the field and the velocities don't remain constant as the distance from the sun increases. What if instead of being perpendicular, a charge's velocity was parallel to the magnetic field? In this case, you would get no deflection at all. Now imagine that the velocity is both parallel and perpendicular to the magnetic field. That is, it's at a diagonal. In this case, the parallel component would be undeflected, but the perpendicular component would be forced to move in a circle. It would be a circle and a straight line. That is called a helix. You might be wondering, what is the good of this magnetic force? What can we actually do with it? I have here a copper wire, which is a conductor, and it has charges in it that are free to move. I'm going to move it toward the magnet. It's going to generate electricity in the wire. Watch the light bulb. Just by moving this loop of copper over this magnet, I am generating electricity. This is how electricity is generated at almost every power plant in the world. Now, what do you think will happen if I instead move the magnet? The same thing happens, just so long as the two objects are moving relative to each other.